On September 12, 1962, the President of the United States, the late John F. Kennedy, made his famous speech about landing a man on the moon by the end of the decade. At this point, NASA has just several hours of human spaceflight experience. Americans had accepted the space race would be won by the Soviet Union, who had already claimed the records for launching the first satellite and the first man into orbit. In order to achieve their goal of reaching the moon, NASA would need to develop a much larger rocket with engines more powerful than they ever did before. But scaling up to a much larger rocket design sent NASA engineers into a new world of complex problems. In this vlog, we will be tackling the problems encountered by the scientists during the space race regarding combustion instability in developing new rocket engines, especially kerosene-fueled engines. Developing a new rocket engine on a much larger scale is extensive and expensive at the same time. A few reasons for this is that developing a new rocket engine needs the ability to capture detailed measurements of combustion dynamics, a physical understanding of unstable combustion mechanics, and a high-quality data to draw hypotheses. The reasons why people in the 60s were able to develop a kerosene-fueled rocket engine, like the Rocketdyne F1 engine used in the Saturn V rockets that took Apollo astronauts to the moon and back, is by using heritage design and extensive development of tests to provide reliable and high-performing engines. So, there are actually several types of engine cycles used in rocketry, but in this video we'll be focusing on the staged combustion cycle, specifically the ORSC or the Oxidizer-Rich stage combustion. I think I forgot the definition of the Oxidizer-Rich stage combustion. I think I have to ask Nora about this. Hi Nora, I would like to ask if you know about the Oxidizer-Rich stage combustion engine cycle.
Uy, Brendan! Hi! So, Oxidizer-Rich state combustion engine cycle offers improved cycle efficiency and density-specific impulse by using hydrocarbon fuels with an oxygen-rich pre-burner exhaust as the oxidizer, unlike the other engine cycles. So, this type of staged combustion engine cycle started in 1959 and developed by no other than the United States' biggest competitor during the space race, which is Russia. So they developed the NK series engine by Kuznetsov Design Bureau and the RD series engine developed by the Energomash Enterprise. So these two series represent the most well-known, reliable, and high-performing ORSC engines. So despite its advantages, the ORSC cycle also presents many challenges associated with achieving high performance efficiency.
So another question are, so what are the challenges in developing an ORSC cycle?
So one of these challenges is its high main chamber pressure that results in increased heat flux or its thermal energy transfer from one substance to another per unit time and area denoted by temperature change. Second, it requires increased cooling and specialized materials to handle aggressive oxygen-rich environment. And lastly, an increase in risk and severity of combustion instabilities. The most well-known example of combustion instability happened during the development of the F1 engine. So in order to lift the enormous Saturn V rocket, required 5 F1 engines on the first stage and is capable of producing 1.5 million pounds of thrust to achieve this amount of thrust. So massive amounts of RP1 fuel and liquid oxygen had to be pumped into the thrust chamber.
So since it's producing that much thrust, how much fuel does it burn?
The first stage can actually burn an Olympic swimming pool's worth of fuel in just over 2 minutes. So imagine how powerful that engine is. So now let's go back in history in 1962. Rocketdyne was ready to perform a long-duration test of F1 engine. So as the test started, the turbo pumps pulled up and the test came to a catastrophic halt because the engine exploded due to a combustion instability.
So wait. So what is combustion instability?
Combustion instability. Okay, wait ha. Let me search. Okay, got it. So, combustion instability is where the propellants in the thrust chamber burn unevenly and cause enormous pressure swings inside the chamber. So, since an engine with a scale had never been made before and the solution to the problem was not obvious. So, later on, engineers started to focus on the injector plate, which feeds the fuel and oxidizer into the thrust chamber. So the engineers also took inspiration from the V2 engine to solve the combustion instability problem for the F1 by adding a series of baffles to the injector plate to split the combustion up into different zones. So soon enough, the engine was able to execute a flawless burn. Now let's talk about the prime example of Russia's high-performing ORSC engine, which is the RD-170. Like the F1, it also underwent a similar intense development comprising a subscale and full-scale test and analysis to yield a stable injector design like the F1's baffle elements. So the RD-170 main chamber injector consisted of several types of injector elements, and its primary injectors are the GCSC or gas-centered Swirl Coaxial Injectors, which are combustors designed to be unstable. So this type of combustor encouraged the development of several validation studies as well as development of single-element tests to design a multi-element combustors that would become unstable spontaneously.
So what are the parameters that gas-centered swirl coaxial injectors have that affects the dynamics of mixing and the reaction between fuel and oxidizers?
The critical design feature of GCSC includes the oxidizer inlet geometry, oxidizer tube length and diameter, geometry associated with fuel injection, injector recess, and the diffuser cone geometry at the injector face. The main chamber also included baffle elements that extended into the flow from the injector face to help dampen tangential acoustic mode oscillations. So, you might be wondering, why am I discussing all those things in this video in a hypersonic manner? So, the reason behind it is that we will be analyzing a journal entitled Detailed Measurement of Oxidizer-Rich State Combustion Injector Dynamics in Model Rocket Combustors by M. Bernard, R. Gejji, and W. Anderson. So in summary, their paper presents experimental results from a model rocket combustor that uses a gas-centered swirl coaxial injector element injecting warm oxygen and ambient temperature RP2 fuel with 900 psia chamber pressure, representative of an oxidizer-rich state combustion cycle. So, the study wanted to validate the data from two combustor configurations using warm oxygen-rich gas and ambient temperature RP2 fuel. Their study also used the technique feature of the RD-170 injector config 1 using GCSC injector and features beveled contour between the injector recess and the main combustion chamber, and then the config 2 same injected configuration but without the truncated cone, so that the injector ended at a sudden expansion at flat face inlet to a cylindrical combustion chamber, typical in Western Europe and United States design. Moving forward to their experimental design, the proponents wanted to acquire validation quality of datasets of a single injector element combustor to test computer simulation. Proponents also designed the Model Rocket Combustor to enable high-fidelity measurements of pressure and flame light emission with well-defined and well-characterized boundary conditions that can simulate or model. The main focus of the study is the high-frequency pressure field that provides direct quantitative measurements and compared to simulation results. The ignition is achieved in the pre-burner and combustion chamber via hydrogen-oxygen spark augmented torch light igniters that are extinguished after ignition of the main propellant flows, which is inexpensive, simple to operate, and is reliable. The computational modeling of the environment will be facilitated by a sonic boundary located at the oxidizer manifold inlet and a sonic nozzle located at the combustion chamber exit. The proponents also used a thermal barrier coating made OSAT of Etheria stabilized zirconia and will be applied to all surfaces downstream to reduce heat transfer to the walls and approach adiabatic conditions where there is no heat transfer between boundary layers. Lastly, they also used an array of thermocouples embedded in the chamber to approximate heat loss in the system.
Okay, Nora. I think I get it now. Thank you. So, as what I said earlier, the study used two configurations, the typical flat face injector and a beveled face injector, in which there is a conical expansion between downstream of the injector recess. So the bevel design was inspired by the RD-170 main chamber injector. So moving on to the results of the paper, analysis of the pressure data recorded from the selection date validation case of each configuration is compared to the target value. The three computational modeling was performed by the proponents, and let's tackle them one by one. And I think I know who to call.
Then I'll call the Space Cowboy.
Hi AJ, I'm now discussing the three computational modeling that was performed by the proponents for my blog. So do you want to say something about it?
Right now, I'm in the middle of my otaku conference, but computational modeling. Yeah, I have facts and something to say about it. So where can I start? So in the first computational modeling, where the proponents analyzed the combustor performance, they summarized each configuration by an amplitude of dominant longitudinal instability modes. In the combustor, based on a calculation of the power, spectral density, chamber pressure signals, the test started with ignition of oxygen pre-burner that generates warm oxygen that is injected through a choke of distribution plate and allows to stabilize before ignition using the torch igniter. Study found out that a relative low amplitude bulk mode fluctuation near 320 Hz was observed at all measurement locations. Later, they found that there were no correlation between the high frequency oscillation amplitude and the bulk mode oscillation amplitude. Lastly, the total heat loss was estimated to be at 1% of the total flame energy release, thus the adiabatic wall assumption may be adequate. The power spectral density or PSD of pressure within the signal in the combustor indicates the average signal power associated with specific frequencies. The PSDs of the oxidizer manifold and oxidizer post pressure reveal nearly identical frequency content in both injector configuration because the oxidizer manifold post geometry and gas properties are closely matched. In each configuration and coupled interactions with the combustion chamber was minimal. The most striking difference in the spectral signature between the two configurations occur immediately downstream of the recess. Lastly, during the final PSD of the pressure test, at the measurement location, pressure is measured at the total chamber wall diameter in both configurations. Higher frequency content excited near the injector faced by the beveled injector gradually dumps out. Power spectra at the chamber AFT and indicates similar response between configuration compromising primarily acoustic model content. The following tests involve the longitudinal pressure mode shapes, the concerns, the flame change response to the chamber acoustic model. It is shown by the power spectral density analysis that changes in amplitude of the oscillation at longitudinal mode frequencies occurred at different axial locations in the combustor. The nature of the fundamental longitudinal pressure mode shape is revealed by applying zero-phase Butterworth bandpass filter to the pressure data centered about the measure in the first longitudinal mode frequency with a 5% cut-off bandwidth. The test showed that the reduction in local amplitude of the acoustic mode, the bevel injector configuration occurs near the expected location of higher energy releases near the injector phase. And that's it. That's all I can say about it.
Thank you for that, Space Cowboy. The study involved the multi-resolutional analysis, which involves the continuous wavelet transform analysis, and the fractal and multifractal analysis. The study concluded that in each configuration, dynamic pressure signals varied minimally in the oxidizer manifold, oxidizer post, and fuel manifold measure locations, given certain parameters. So just like in any study or any test, comes with these analyses to find more data on each configuration. We have now reached the ending of this vlog. I was able to learn different things starting from the development of F1 and RD-170 rocket engines. I've also learned about the problems encountered when making a new rocket engine, especially the difficulties of combustion instabilities. I also learned about the solution made by the engineers in the 1960s that addressed the combustion instability that brought man to the moon. So thanks to my friends Nora and AJ. They were able to enlighten me regarding the gas-centered Swirl Coaxial Injectors, as well as discussing the journal Detailed Measurement of Oxidizer-Rich Stage Combustion Injector Dynamics in Model Rocket Combustors. Thank you so much in helping me in this vlog, and I'll see you in the next one.